Hey stats students, Ms. A coming at you with another video again. Today we're going to be starting Unit 1, Lesson 8 about normal distributions. This is sort of picking up where we left off in Lesson 7. In Lesson 7 we talked about these ideas of model distributions, these sort of mathematical functions that we can use to approximate real-world distributions. We originally took a look at the uniform distribution because it's pretty easy to work with. Today, though, we're going to start looking at the normal distribution because it is probably by far and away the single most widely used of our distribution functions. It's going to be popping up all over the place throughout AP statistics and in anything else statistics related that you might work on. So we're going to go through an example. We're actually going to see sort of from start to finish, like how do we come up with a model from a problem? What do we do with it? And hopefully this will kind of show you why this is useful and what we can do with it. So here's our scenario, and this is kind of a bit true to life. Staff and students who enter Harlem Renaissance have to have their temperature read by an infrared thermometer. I guess this is true for like lots of schools and restaurants and any kind of public places now. And by infrared thermometer, right, we're talking about those thermometers that you like hold up to someone's head and they kind of read the amount of infrared radiation coming off of your head to get a sense of how hot it is. And sort of very true to this, every time I go in, I see with myself, with other people, that there's a lot of variation in the measurements, right? If you step up to it, step back, come up again, you might get very different results. And also, like, they tend to be a little biased towards, you know, one direction or the other. And so this kind of would get my statistics sense tingling and kind of trying to think about, well, like if these thermometers are consistently underestimating, right? They always tend to read very low, like 94, 95, 96 degrees rather than like 98 as we should get. Then it kind of bugs me. I'm wondering like, wait, so you're telling me like if I came in with 100-degree temperature, I still might get a reading less than 98. You know, so like, is this actually going to capture a fever or not? So this is kind of like a real legitimate question we might be trying to figure out. So, you know, to the statistics mobile. So Miss A, being her wonderful nerdy self, gets one of these, borrows it from the school nurse. She also gets a hospital grade oral thermometer. So, just one of those regular ones with the little digital readout that you stick under your tongue, right? That's sort of like the gold standard right now. So, right, the idea is I take my reading, and this is my idea of like, this is my true current temperature according to this thing that I am confident in. So I get 98.1 degrees Fahrenheit, and I'm, this is going to be my baseline. And so what I want to measure is essentially how different is the IR thermometer reading from the real temperature. So as you can see in the table, right, so 20 measurements are taken, and so we see the temperatures in those kind of top two rows. Those are the different temperature readings. And then the bottom two is sort of where I took each of those temperature readings and then subtracted the baseline. So I'm trying to get a sense of like underestimating or overestimating. So for instance, the way we would read this is this value of 97 so if the IR thermometer read 97.5 degrees, that means it underestimated the temperature by 0.6 degrees, right? It came in at 0.6 below the baseline. And so all of these are those differences, right? So we see a lot of these maybe underestimated by somewhere between 2 and 3 degrees, right? We're kind of seeing a lot of underestimation, right? They're all negative numbers. Like not a single one of these came out above the my true temperature. But that's all I can really say from this. And, maybe I can graph a histogram of this. I can get a sense of the shape. But I can't really answer too many questions about this, right? I could say sure, if I did another reading and it did overestimate, right? I could tell that that's pretty unlikely. But I don't know how unlikely, right? Maybe if I repeated this for 500 measurements, I would get some overestimations. Maybe it's just the fact that I stopped at 20. So this is where a model distribution is really going to shine. So what I did was I go into Google Sheets and I made a histogram. If you're really observing here, you'll notice it's actually a bar chart because it's got those gaps in between. I kind of sort of had to fudge it and do my histogram as a bar chart just because that's the only way to sort of do this in Google Sheets, where I can also put the graph on top. So here's the idea, right? I found the mean difference, right? So if we look at this data, the mean of these differences was 2.56 degrees. The standard deviation of those differences was 0.95 degrees. So here's the histogram, and based on this mean and standard deviation, I constructed a normal distribution. Don't ask me how, we can get into that, but I constructed one, and as we can see, it actually lines up pretty nicely, right? The red line is where we would hope for it to be, right? We kind of notice it's always in line sort of with these top left corners of the histogram values. So it's very close. It is, and this tells us this is probably a good model, right? We make this normal curve and it's basically giving us our original data back. So I'm gonna go ahead, say this is a pretty safe place to use a normal curve to act as my model, and we're gonna go ahead with that. So the kind of first thing we can do with a normal distribution is, right, the normal curve is a very kind of standard curve. Like I said in the last lesson, people have been studying this curve for 400 plus years at this point. Well, maybe not quite 400, somewhere between 300 and 400 years. So we've studied this quite a lot. We know how it behaves. So one very common way of using these things, and this is not a calculation you have to do by hand, this is purely something you can do with common sense, is we can use these standard deviation measurements, right? We kind of did this a bit when we talked about z-scores in lesson 6. We sort of measured how, if I have a value and it's some distance above the mean, we can calculate its distance in terms of standard deviations. We can say, oh, this value is 1 standard deviation above the mean, or this other value is 1.5 standard deviations below the mean. And we can kind of do something similar here with our normal curve. If we start at the mean in the center and we start going out in both directions, so we're always going to be looking at the middle of the distribution. So if we go out to both the left and the right by 1 standard deviation, that middle area, right, this middle area right here in between the minus 1 standard deviation and the plus 1 standard deviation will be about 68% of the distribution, which is, pretty close to 2/3. So that 2/3 is a very rough way of expressing that. It's closer to about 68%. As you can see here, a little more accurately, it's about 68.3%. But, 68 is how most people remember it. If we go out now a little further, so between 2 standard deviations below the mean over here and 2 standard deviations above the mean, this will capture about 95% of the data. So 95% is in here, while only, so the remainder, the 5%, will be in these tails out past the 2 standard deviations. And as a shorthand, because the term standard deviation is just like, it's a bit of a mouthful to say over and over again, a lot of times we just abbreviate it with the symbol that we use, which is sigma. So I might say between -1 sigma and +1 sigma, that means -1 standard deviation and +1 standard deviation. So if you hear me using sigma, I'm referring to the standard deviation. So the last number is, well, what if we go out 3 standard deviations? In lesson 5, we actually used this as a way of testing for outliers, right? We kind of said that, like, if you go out to 3 standard deviations or more, you can pretty safely call things outliers. And here we can see why, because 99.7% of the distribution should be somewhere between -3 sigma and +3 sigma. 3 standard deviations below, 3 standard deviations above. So if you go out further, that literally leaves about 0.15% over here and 0.15% over here. Very, very, very small. Like, very rare that we're ever going to get anything out this far. Maybe 1 or 2 things. And that's kind of our definition of an outlier. I had said in that lesson as well that sometimes if you really want to push it, you could do it with just 2 standard deviations. And here, you know, you're going to leave out the lower 2.5% and the upper 2.5%. So, you know, even that is fairly rare, but whether it's rare enough to call those outliers, that's where we get a bit iffy. Whereas here with 3 standard deviations, where we are talking about now fractions of a percent, small fractions of a percent, that is rare enough that pretty much anyone would agree to call those outliers. So this is the idea, right? So we can come up with, okay, this middle whatever amount of data is going to be, so the middle 68% will be between here and here. Middle 95% between here and here. So this is really good for coming up with, you know, sort of margins of error. This is actually something we're going to do, you know, quite a bit down the line, but we're going to see the beginnings of it here. So Miss A presses forward, right? She makes her normal model. And she starts with the -1 and +1 sigmas. So she does her calculation. If you go 1 standard deviation below the mean, we get a difference of -3.51 degrees. And if you go up above the mean by 1 standard deviation, we get 1.61 degrees, negative 1.61 degrees. So what I can say is that about 68% of all of my readings are likely going to be within this interval. Or another way of saying that is, you know, there is a 68% probability of a reading having a difference that falls in this range. So this is kind of a way of expressing like confidence, right? It's definitely better than 50-50. Not much better, but like 68% chance it's not too bad, right? I can express with a certain amount of confidence, I think that for any reading, the difference from the true temperature will probably be somewhere in here, somewhere between like 1.61 and 3.51 degrees lower than the real temperature. It's some amount of confidence. It's not necessarily a lot, but it's some. So what we can do is, right, we can start pushing out to 2 standard deviations, 3 standard deviations, and we are going to capture a lot more of our potential readings. So what do we get here if we do that pushing? So 95% of readings are likely to have differences between -4.46 and -0.66 degrees. Or that's like saying that I can predict, if I take my temperature, that it will be somewhere between 0.66 degrees below my actual temperature up to 4.46 degrees below my actual temperature 95% of the time. Or I can say, right, I can predict it will be in this range of values with about 95% confidence. And then last but not least, say like we can really push our confidence by trying to capture a lot of the distribution, right? We can say like almost the entire distribution. Like 99.7% of all of these differences will be somewhere in this region, from negative 5.41 degrees to plus 0.29 degrees. So actually overestimating the temperature. Okay. But so these give me kind of different windows, different ranges of values where I can predict or I can expect my results of future readings to fall. And, you know, this is tied to the level of confidence that I want in them. So, you know, if I want like 95%, I can use this interval, say, my values are probably going to be in here. Or if I want like this level of confidence, 99.7%, I can do these. So like this can be really useful. If I want to kind of express, here's where I expect things to be, kind of between here and here. So this kind of starts begging more interesting questions though, right? Like finding those intervals is great. Being able to express that confidence is really cool. But here's one thing that I noticed in all of this. With my real data, I never got a difference that was above 0. But when we look at this normal model, and especially when we notice this 3 standard deviations, actually our model is going to predict that some readings will overestimate. They will have a difference over 0. So now the logical question that, you know, a nerd of Miss A's caliber will have is, well, what's the probability of that happening? What is the likelihood that I will overestimate the real temperature? Or to put this in more of statistics terms, in terms of our model, what's the probability of getting a reading where the difference from the baseline, the difference from the real temperature, is greater than 0? So this gives us a much clearer mathematical question than just asking what's the probability of overestimating. So let's kind of look at this. So here's our normal density curve for this situation with our mean of negative 2.56, standard deviation of 0.95. So if we're talking about like readings where we are overestimating, that is this tiny little shaded tail above 0. We can kind of tell, right? Remember, the probability of something happening is what percentage of the total area under this curve is taken up by this interval. And we can already tell it's going to be a small percentage, right? That shaded area is tiny compared to the rest of the graph. But how tiny? Like, can we get an exact percentage? In fact, we can, using a calculator, or in our case, Google Sheets. So most calculators, and Google Sheets is included in this, the most common way that they do these, so this is using what's called a cumulative density function. We talked about cumulative frequency and cumulative relative frequency back in lesson 6 about percentiles. So now we're just applying the same kind of idea, but now to density instead of relative frequency. We're basically like kind of saying, okay, if we start from all the way at the left at like negative infinity, and we start going up and 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 up to a given value. Let's say we go all the way from negative infinity up to negative 2. Like we can say, okay, the cumulative density up to this point is something. So it gets the area to the left of a value. It's starting its accumulation sort of from all the way at the left end of the number line up to wherever your value is. So it's usually they will calculate to the left of a value. In our case right now, though, we're trying to find it to the right of the value, but we can still kind of use this. So in Google Sheets, if you want to find the area under this curve to the left of a value, right, so less than a value, we use the norm dist, right, normal distribution command or formula. This needs to be given 4 things, and you have to include all 4 things. What is that value that you're looking at? Our boundary values, say like -2, or in our case, 0. What is the mean of the distribution? What's the standard deviation of the distribution, right? Any normal curve needs both of those. And then we need this last thing that says true. And this is what tells it to treat this like a cumulative density function rather than just giving us regular density. So you have to include this true. If you don't, it will assume you meant false and will give you a whole different wrong answer. You have to include the true. So let's put this into practice. So I can go to Google Sheets and I can use the norm dist formula to find the area to the left of 0 as kind of shown by this graph here, right? So it's all this area up to 0, starting at the left and going up to 0. So I do it this way, norm dist, I use 0 as my boundary value, -2.56 for the mean, 0.95 for the standard deviation, and true to get the area. And when I put this into Google Sheets, the answer it gives me is 0.9965. So we can think of that meaning this area represents 99.65% of the total area, which makes sense, right? This looks like almost 100%. There's just this very, very, very tiny little thing that's not included. But again, we want area to the right, not area to the left, just like in this one. But we can use something to our advantage. We know all density functions, if you find the total area from all the way on the left to all the way on the right, from -infinity to +infinity, the total area will be 1. So that means the area to the left of 0 and the area to the right of 0, if we combine them, they should give us this total of 1 because it's the whole distribution. So now we know the area to the left is 0.9965. We know the total density, or the total area, is 1. So just doing a little algebra, the area to the right is 1 minus 0.9965, which gives us a result of 0.0035 or 0.35%. So what this is telling us is, if I were to read my temperature with the infrared thermometer, only in about less than 1%, only in about 1/3 of a percent of my trials with this, like I could do this 100 times and still not get an overestimate, but maybe if I do like 300 times, I'll probably expect to get an overestimate once, right? This is a very, very rare thing to have. This is a very low percentage, to just be 0.35% of the time. So, in conclusion, right, I want us to think about this not just in terms of the formulas we can now use, right, the norm dist function, or the kind of calculations we can do, right, finding area with a CDF. And I want us to kind of think about, grand scheme of things, what have we gained by using this normal model instead of just the original data? So after I had the original data, I could only tell a few things. I could tell, well, all of my observations had a difference less than 0. That means it's consistently underestimating the real temperature. I could tell the average. I could say, okay, on average, it's underestimating by about 2.95 degrees, or sorry, 2.56 degrees. I could even get the standard deviation to get a sense of the variability. But that's really about all I can say. All I can really talk about is that sample, the 20 readings that I did. I can only speak for them, really. Now, though, when I use the model, now the model is really telling me about like any potential future result, or say like what my results might look like if I did thousands of readings, like millions of readings. And they let me do a lot more specific things. So in particular, we did two things. First, we came up with these intervals where we could expect most readings to be. And to do that, right, we could find, say, the middle 68% by going out one standard deviation to either side. We can find sort of the 95% by going 2 standard deviations out from the mean to either side. Or we could find the 99.7% of expected things from 3 standard deviations out, either below or above the mean. So this lets us give windows for our estimates with kind of different levels of confidence that we can specify, because we know 99.7% of our observations should come in here, right? So if I guess every single time that it will be in that window, I will be right, hopefully about 99.7% of the time. But again, this is a topic that we are going to go into in a lot more depth in future units. The second thing, the one that we are more immediately going to be using, is this idea of calculating exact probabilities, the exact probability of getting a future result that is less than some value or greater than some value. Say in our case, we did this with differences. So we could say there was a 99.65% probability of an underestimate. There was a 0.35% chance of an overestimate, right? The first one is differences less than 0. Second one is differences greater than 0. And this works for a lot of different things, as we're going to see in the lesson activity, which we will be doing in class together. Or which, if this is in the future, you might be making up on your own. So we get to find these really nice exact probabilities of getting different kinds of results, especially kinds of results that we did not get in our original data. If I'm looking at my original data, I did not get a single overestimate. So in my mind, I'm thinking there is 0 chance based on this data of getting an overestimate. But reasonably, I'm thinking, well, the underestimates aren't that huge. Some of these are really close to 0. But because I didn't get any data with overestimates, I have no way of establishing the likelihood of getting an overestimate. That, though, is something we can do with the model, right? If I say this model is a good stand-in for my data, then if the model says I have a 0.35% probability of being greater than 0, then I should expect my real world data, my real samples, my real measurements to follow a similar probability. And then when I actually take the measurements, to kind of have a relative frequency represented by that probability. So again, we can start making predictions. We can ask questions about potential readings, potential values that didn't exist in our original data set. And so we've already kind of really expanded the types of questions we can ask and answer, which is always the goal of what we're doing with statistics. So, after this, please take a look at the Lesson 8 activity. We will be working on it together in class, but if you're making this up, please try it out. Hints are available in cell M285. Please make use of the hints. If you are not one of my students and not in my class and you enjoyed this, leave a like, leave a comment. If you have a question, feel free to ask me. I might actually answer you. But thank you guys so much for watching, and look forward to our next lesson.